saying really basic stuff and you're all bored, then please put your hand up and say, get on with it. I'm very bored. And I'm going to sort of do this really to use the language that I'm familiar with, the language that Pascal Chaussat used in his presentation in the workshop week, the language that is available in excellent textbooks. And I have some lecture notes as well from when I did a set of lectures in this room 7 years ago for graduate students. And the difference between those lectures and what I'm going to do now is that I actually prepared the stuff 7 years ago. So, okay, still too long. So this is symmetric bifurcation theory as a topic, and I thought I would just sort of start by, so a lot of this liquid crystal stuff is couched in terms of free energies and things evolving to minimize an energy quantity. This is a different, more general viewpoint where I think about dynamics the whole time, because maybe I don't have a free energy. Okay. So in the absence of symmetry, then we have ideas of generic bifurcations. Okay? So these are commonly called saddle node, for which there's a sort of canonical model equation in one variable x dot is mu minus x squared, or an oscillatory bifurcation, sometimes called hot bifurcation, with one complex coordinate z dot mu plus I omega z plus or minus z mod z squared. Okay, so these are kind of canonical normal form equations for these different kinds of instability, starting with minimal assumptions about having an equilibrium point that exists at the origin x equals 0 for a parameter value mu equals 0 and undergoing some change in stability.
Yeah, okay. Mu is your bifurcation parameter.
Yes, so my usual notation is always going to be x dot is f of x and mu. Mu are going to be the parameters, usually only one parameter, and x will usually be in Rn, although it should be obvious in the context, and if it isn't, then you can either turn to your neighbour or you can ask me.
But of course in liquid crystals, x are the order parameters.
Yeah, hang on. It's just there's no interpretation of this yet. Yeah. Okay, so it's a dynamical system, so it's a state space and an evolution law. So what is my state space is going to be Rn, which is going to be a collection of values of order parameters. Maybe I should say that at the beginning, okay? We don't need to know what the order parameters represent in a non-technical sense, okay? And then there's a dynamical system is a state space and an evolution law, and my evolution law is given by the flow of this vector field. Okay. So these are these simple examples are. They're simple because they only involve one parameter, and the usual sort of technical term for this is to say that they are codimension 1 bifurcation. So I vary a single parameter, and I see one event that happens at mu equals 0, and we would like to kind of extend this idea of the simplest kind of bifurcation to the case when I'm constrained by symmetry. Okay, so I have to motivate how to get symmetry into the problem. Okay, so symmetry is going to do lots of complicating things, okay, because it's going to give us a new idea of what it means to be a generic bifurcation. Okay, and the simplest example would be just the constraint that f was, for example, an odd function for values of mu, okay? And as we know, that gives us a pitchfork bifurcation as a generic change in the stability of the origin in 1D rather than sans mode. Okay, so this is a constraint that changes my idea of what is generic for a bifurcation. Okay.
Sorry, John.
Yeah.
Do you assume that x equals 0 is a solution for all mu in general?
In general, no. It's a consequence of this constraint that it is in this problem, but it's not in the other problem necessarily. I mean, it is in the Hopf case, the way that I've written it, and it is, yeah, the solution branches are only at the origin when mu is 0 in the Southern Mode case. But one can start by supposing that there is a single parameter. When that passes through some critical value, there is an equilibrium point that is degenerate in the sense of having a Jacobian matrix with a 0 eigenvalue, and then proceed from there. Okay. So an intuitive idea of what a symmetry would mean would be some kind of informal statement like the following. So G of x of t is a solution trajectory of my ODEs whenever x of t is a solution trajectory then G is a symmetry. So this is actually easier to kind of state in maths, as it were. So if G of x is a solution trajectory whenever x is a solution trajectory, then what do I have? So Gx being a solution trajectory means that f of gx must be ddt of gx. And then g is going to be some operation that is time independent. So this is g times ddt of x. Okay, so this is g times f of x. Okay, this is for all x. So in other words, f of gx, well, let's write it without the brackets, is equal to g of fx. So this is my condition, my symmetry constraint, that G, such a G, commutes with my vector field x. Okay? So this equivariant condition, as it's known, is just a mathematical version of the kind of intuition that your problem looks the same when you did something to it. Okay? Well, your solution looks the same, at least. That's true for all solutions. So in the top statement, it doesn't matter whether gx is actually the same solution as the one you first thought of, x, or whether it's a different one. Okay? There's no, I don't need to make that distinction. And then implicitly, in the above, we have G acting on Ra, and in fact acting linearly. So I need some sense of G being a linear map on Rn, so it's going to be represented by some matrix operation. Okay? But I'm going to sort of hold that thought for a moment and rewind a little bit, because there are two separate ideas that I want to make sure are kind of fully separated now, which is to distinguish between a group in the abstract sense and a way that that group might act on a particular collection of order parameters. Okay? So there's a kind of, there's a line to be drawn. for this one. So is everybody kind of really comfortable still? No.
I'm slightly confused by the notation.
Okay.
F is something in Rn.
Yes.
And then if you write GF, is that meant to be a function of F, G of F, or?
So this is going to be a matrix, essentially, and this is going to be a vector.
So you assume from the start that it's a linear function.
In this discussion, yes.
In principle, could be a nonlinear operator from Rn to Rn.
Could be anything at the moment being. I mean,
That'll do as an answer.
It's got a
Thank
clear
you.
differentiation.
It's got, yes, so it's kind of time independent, I suppose. So there are other kinds of operation I can imagine, like time advancing down my solution trajectory, which are, you know, in principle allowed, but they're not what I'm thinking of at the moment.
I mean, what you also could is allow is a manifold, and you have an action on the manifold which need not be linear, because there you would not know what linear means.
Yes.
This is the same setting, but
Yeah.
Yeah. But F is, of course, strictly a vector field. And so the second G there, the GF, is actually the linearization of G applied to that vector field. But if G is
Yeah.
already linear
Yeah,
and you're in Rn, then
Yeah.
it's all the same.
that's right. So I'm using
Otherwise, the differentiation has some problems.
yes. So I'm identifying Rn with its tangent space, I suppose. And so, but I am fine. Okay. Big sigh of relief. Where are we going now? Okay, so I now want to go to the group part of life. Okay. So a group is a set plus a binary operation, and my notation, which is going to be different to any other notation that you've ever come across, is going to be that the identity element is called I, and small letters are going to be contained in big letters. Okay, going to be elements of big letters. So I've got G as a set, okay, with a binary operation that I'm either going to write as a circle, or not write as anything at all. Okay, and it satisfies some axioms that are well known. Abelian groups, every pair of elements commutes, and subgroups are closed collections of the set of elements of G, subsets of G that are closed under composition. So a subgroup N in G is normal if G inverse NG is equal to N for all little g in big G. Okay, so this is a kind of set-wise notation. So I mean the collection of elements G inverse little n G for all n in N is equal as a set to capital N. Okay, it's some rearrangement of it. Okay. So now let's quickly recap cosets, and then I can do quotients, which will be useful. So for any subgroup, okay, so I've just talked about normal subgroups, but now I'm back to any subgroup. Okay, H contained in G, and any G in G. The subset little g capital H, which is just the collection of little g little h for H and H, is the left coset of H. Okay, so this is just a collection of when I start with the subgroup H and I think about every element in capital H acted on by G, Okay, that's not a subgroup, but it is a useful object. So I'm not going to, following result is worth proving, but it's not hard, so it's going to be left as an exercise for people who would like to do it. Yeah, so I suppose it really deserves lemma. Distinct cosets partition G. Okay, so implicit in this statement is the fact that any two cosets are either disjoint or they are the same. So I can write G as a collection of objects of kind of subsets H, which is H times the identity, G1H up to GKH, okay? And that's just a kind of reordering of all the elements of G. Then, if I happened to choose an H which was a normal subgroup, okay, then this collection H, G1H, etc., up to GKH, in fact forms a group. So this collection of cosets forms a new group under a new composition element, composition operation. Okay, so I can define a new way of composing things, composing cosets, G1H, okay, new operation G2H, and this is defined to be the coset G1, G2H. Okay? So this is technically a different composition operation to the little circle that I had, which was a composition of group elements. This is a composition of cosets. So it's a group. So we can write G quotiented by H for the set of elements I, G1 up to Gk, which will multiply my cosets with the binary operation star. Okay, so this is it's a new group. It's a quotient group or a factor group or something. So this is useful because I can define this thing that people call normalizer. Of H. So H is a normal subgroup.
May I ask a question? And how can it is always true, or can we be sure that G1, G2 of H was among the chosen ones that made G in the second line? When
Yes.
we, yeah.
Yes.
Okay,
This is so.
that new operation is closed
Yeah,
in the new.
that's right.
In
Big
principle, it's
lemma.
not obvious.
This operation makes sense. This is well defined. Okay, we need to show that. Then we need to check the group axioms, and it all works. Yes. It's an excellent homework problem. Yeah. So it's all true. I'm just not going through the details because I mean we can make this a kind of 2-week course, but nobody wants it. But yeah, this is all true because there are good people in the audience who at the moment have not shouted at me, which is excellent. And hopefully I've set things up so that they're, you know, it's a pretty standard development. Yeah. So, but there is plenty to check here. I'm stating the answer. but there is a lot to check that things do not go wrong.
Can I make an observation about normal subgroups, which
Yes.
I found helpful when first, well, not when first meeting these things, I was quite mystified, but when later
Yeah.
on thinking about it,
Yeah.
is that in some sense, if you're thinking of a group action, a normal subgroup often corresponds to something which is geometrically intrinsic. And the example I always think of is the Euclidean group of Euclidean motions in the plane. You've got a subgroup of, if you've got an origin, you've got a translation, you've got a subgroup of rotations about the origin,
Mhm.
you've got a subgroup of pure translations.
Yeah.
Now the subgroup of pure translations is normal because
Yep.
if you take the plane and you do something, do a motion to it, you can tell it's a pure translation. Whereas the Euclidean motion of the plane is a rotation or not, depending on where you put your origin.
Right.
And every Euclidean motion of the plane, apart from a translation, is a rotation about some point. If you fix your origin, it's different. So rotations about the origin form a subgroup, but if you weren't showing the origin, you were just showing the plane, you wouldn't know about the rotations. Whereas if it was just a pure translation, you would know geometrically that that's what it was.
Mm-hmm.
And the consequence is that if you factor out the translations, take the quotient group, you just get a rotation group. So every Euclidean motion of the plane has a rotational component. You can say what the amount of rotation is, but you
Yep.
can't say where it's about.
Yep.
Whereas it does not have an intrinsic translational component. So the translations and the rotations are sort of both subgroups. One of them is kind of stronger than the other one, and it's a normal subgroup.
Yes, it's more natural than the other.
It's more natural,
in
and
some
it,
sense.
and it sort of doesn't depend on some arbitrary choice of axis
Yep.
or origin or.
Yep. I was going to do that. We can do that as an example.
I'm sorry if that was.
No.
Right.
It is. It's right and proper that it needs to come up. I was going to get slightly further through the definitions, and then use that to illustrate that.
Fine.
So maybe you could sort of jump in and we'll have a bit more terminology that we can use at that point. Okay. Everybody else broadly happy. Broadly happy. Some people looking distinctly happier than others, I have to say. Okay. Where are we going? So there's a normalizer. Okay, so if I pick a normal subgroup H, okay, there's a normalizer object, n sub g of H is defined to be the set of elements in G such that G inverse HD is in H for all little h. So it's the set of elements in the big group, okay? So ng of h might well be bigger than h, okay, that commute with everything in the subgroup, the normal subgroup that I first thought of. Okay? So clearly h is contained in ng of h. Okay, so the normalizer is at least as big as the subgroup that I first thought of. Okay, and h is normal, so it makes sense to quotientify it. So, with apologies for notation, Q, which is n of h with h quotiented out, is a well-defined object. Okay, so there's a kind of thought to hold on to from that as well. Okay. So, we're going to go a little bit further with the abstract stuff before we get into something more concrete. So quite often the kinds of groups that we're going to be faced with will, as David has pointed out, have a kind of natural internal structure. So there are two sort of natural internal structures that are well worth defining. These are going to be so let's do the direct product first. So these are the direct product and the semi-direct product. So a direct product, so I'm going to suppose G contains subgroups H and K, which have the following properties. Okay, H and K are both normal. Their intersection is only the identity element. And any little g in G can be written as a product. G is little h, little k, with little h in big H and little k in big K. But then there's something else to prove here. Elements of H commute with elements of K and vice versa. So it makes sense to write G is isomorphic to this direct product of H with K. So in some sense, if you have a pair of normal subgroups that break all the elements of G up into something in the first normal subgroup composed with something in the second normal subgroup, then that sort of partition works for the whole of G. Okay, so G as a structure looks like a collection of elements in H, sort of looks like everything where I take any element in H composed with any element in K. So that's the direct product idea. Maybe you don't have all that structure available, but you have most of it. And a kind of weaker idea is a semi-direct product. So G contains subgroups H and N, so that N is normal and H intersect N is only the identity. And every G in G can be written. And G is NH. N and N, and H and H. If so, then we write G is H, semi-direct N. Okay? So this is a kind of cross with a bar down one side, which is my preferred notation for semi-direct products. And the order matters here, okay? Because N is the normal bit. And so the open side of this cross symbol is pointing towards N because it's on the normal side, as it were. Okay. And in fact, if we have this decomposition, then the decomposition here is unique, which is quite nice. There's only one way of writing every element G. For every G, there is a unique N and H, so that this is true.
is that, I'm sorry, is that order the way you want it? You say G is NH, but when you write the direct product, you write H product N.
Yes. So this, sorry, the order here is, so my composition order, I'm always at least thinking that I'm going to do the rightmost element first when I act on something. Okay? In writing this, I've just tried to draw your attention to the fact that N has a property that H does not have, namely that N is normal. Okay? So I want to, this symbol is oriented in a consistent way to do with the placement on the page of H and N. Okay? So I'm perfectly, you know, it is also completely legitimate to write this. Okay? But the, yeah. I haven't seen this just because it's another text symbol. Okay? So you find this one in the manual, and then you kind of always just remember to write things this way around because that's the symbol you can remember in tech. Have you seen this one? I mean, presumably it's whatever this is, you know. Anyway.
The difference in the hypothesis is that one of the subgroups need to be normal. And
Yes.
but that doesn't mean that the decomposition G equals NH is not unique, does it?
It's a semi-direct thing. Here.
Yeah.
If you have something like this, then shall I go through this?
Well, if I'm just
Yeah.
trying to get it straight. If you
Yeah.
write down N1H1 equals N2H2,
Let's do that. Yeah. Okay. Let's justify the last thing I said. So let's say I've got a G which is N1H1 and it's also N2H2. Okay. Then I have H1H2 inverse equals N1 inverse N2.
okay, so that object is in both
Yeah.
subgroups.
So either H intersect N is not just the identity, okay, which is something that I said was not true, or I have H1, H2 inverse is the identity, which is N1 inverse N2, so in fact they look the same. So H1 is equal to H2 and N1 is equal to N2.
So what's the effective difference at the end of the day?
Between what?
Direct product and semi-direct product.
H isn't a normal subgroup here. Only one of them is a normal subgroup.
In this
It's a
case,
commutation.
in this case,
In this case,
the
N and H do not commute.
commuting
So,
distance.
yeah.
Yeah, they do not necessarily commute.
While in
And
the,
H acts on N in general, in general on N.
Yeah,
While in the
but, I mean,
previous case, they can
so the
move.
punchline is that you cannot deduce that G is H cross K, H cross N. Yeah.
Yes. I didn't.
No, you didn't. That's right. No,
Oh.
right.
I spent 5 minutes talking about this stupid symbol.
No, that's okay.
Okay,
Yeah, yeah.
good. Right, move on. Very good.
Yeah. No, I know that it's a different thing. I was just trying to follow the.
I mean, for maybe one
Yeah.
example, we talked about this at lunchtime. If you take Z3 and Z2, and you take the direct product, you get the cyclic group of order 6. And if you take the semi-direct product, you get the dihedral group of order 6.
Yes.
So this is
Yes. Okay, so I was going to. Oh, where am I? Right, I was in the process of getting some more space over
It's normal.
yes.
You can do both products or only one. There should not be the difference, right?
I mean, if you do the same construction, I mean, if you don't know that one of the subgroups is normal and you do the same constructions, then you get
The same.
The same. Yes. You don't have to worry about it.
Yeah, I know that for this case.
So standard notation in the bifurcation world is that Sn is the set of order n factorial of permutations of n objects. Zn is the cyclic group of order n. So in other words, it's a collection of I, G, G squared up to Gn minus 1 generator. Dn is the dihedral group. So this has order 2n, and this has two generators. Suppose it's going to be generated by some pair of objects m and rho satisfying m squared is the identity, and that's going to be rho to the n, and then composed with rho is rho to the n minus 1 composed with n. So that's a presentation of the group. In other words, it's all you need to know. Okay? So it's the generators of the group. There are two generators. I've given you the orders of the generators. Okay, and the only relation you need to make that a finite group. Okay. And so this sort of anti-commute, the fact that n and rho do not commute, means that Dn is going to be isomorphic to a set of, what have I got? I've got Zn, and I've got a Z2, okay, and the Zn's are going to be generated by rho, so that's going to be, so I think I'm that way around. So this is sort of the collection of things generated by rho. This is generated by okay. And then, because David has already mentioned it, we can have E3. So E3 is the Euclidean group. So this is rotations, reflections, and translations. Of R3, and E3 splits up as a collection of things that require an origin, semi-direct product, the translations. So I can translate by any amount, and I can also have my O3 with my rotations and reflections about an origin. Okay, and this has a semi-direct product structure with the translations being a normal subgroup, and therefore a more natural subset. Okay. So this group discussion is completely algebraic. Okay. So just a kind of thought remark at the moment that I've done some stuff that is purely algebra. Now I need to make the connection back to my differential equations that I started with. So I want to think about taking my group structure and embedding that into some collection of linear maps, so I can actually act on a phase space, which was Rn. Okay? And that embedding idea is the idea of a representation. So a real representation of the group G is a homomorphism, which I'm going to call rho tilde. So this is a map from my group G into n by n real invertible matrices. Okay, general linear group. Which one special property. Okay, so being a homomorphism means that composition in GLN mirrors the composition structure that I had available in the group G. So rho tilde G2, rho tilde G1, that's matrix multiplication, must be the same matrix as rho tilde acting on G1, G2. Okay? So it doesn't matter whether I take two elements and I compose them in the group and then I map across to a matrix, or whether I take two elements, I map them across to find the corresponding matrices, and then I must multiply the matrices. Okay? So a real representation is a map from my group to invertible n by n matrices that satisfies that structure preserving property.
Why do you need a word real? This is just a notion of representation.
Because I picked my target here to be real matrices. So this is at this point there is sort of slow divergence from the kind of classical theory of representations for groups, which is developed over the complex numbers. So yeah, and that distinction is useful for bifurcation purposes.
Of course, serious algebraists do it over an arbitrary field.
Do I look like a serious algebraist to you?
Probably a finite field. With,
F star or just F?
let's stick with R.
Okay.
Maybe there's one word of caution at this moment. There is a notion that the representation is of real type, or of complex type, or of quaternionic type. But this word real is not the same as the real representation as you defined it here.
No,
I just wanted to point this out. If somebody comes across these other notions, it means something different.
yes. So we're going to get close to that with irreducibility and absolute irreducibility
Sure.
in the next lecture, I think, given that I can only stand an hour of this. Okay, so exercises for the reader include whatever I do, okay, I need to map the identity element to the n by n identity matrix, okay? And nice things happen. So if I take an element G, I map it across to find a matrix, now I then compute the inverse of that matrix, which I can do because it's invertible. Okay, that must be the same as finding the element G inverse and mapping that across. Okay? So then there is a nice result that simplifies life. So I don't need to work with anything that is in the general linear collection. Okay. Every compact Lie group on Rn may be identified with a subgroup of the orthogonal group with n by n matrices. In other words, I don't get anything more by considering invertible n by n matrices which are not orthogonal. Okay? Orthogonal matrices are good enough. And the kind of counterpart of this is that if I happen to pick a representation of my group, i.e. a collection of matrices that satisfy the homomorphism property, then I can redefine my inner product between vectors on Rn in order to make those matrices orthogonal with respect to that new inner product. Okay? So there's nothing more that I gain by being more general. So in other words, now we can just consider homomorphisms that map me into a collection of orthogonal matrices. Okay. Right.
define what a compact Lie group is, but
No.
never mind about that.
No. I haven't. So this is, tick, 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 cross. Okay? No, can't do this one, hard. The others are all finite, so they're definitely. Okay? I'm going to leave it at that, unless you'd like to take over. Next time. Okay. So, the interest from a bifurcation viewpoint in these representations is always sort of concerned with the idea of genericity. So what is my most likely kind of bifurcation scenario? What is my most typical, my most common bifurcation, subject to the symmetry constraints that I'm building in? Okay, so in the absence of symmetry, I expect to have a saddle node bifurcation. Okay, if there's nothing else special around, it's either going to be a saddle node or a hot bifurcation. Okay, and the kind of irreducibility is getting at what are the simplest kinds of bifurcation I would expect when I have this imposed symmetry structure. Okay, so now this is thinking about how these matrices, okay, these rotildas of G, are going to act on Rn. Okay. Okay. So linear subspace V in Rn is going to be said to be G invariant, or simply invariant, rho tilde G acting on V, so that's in V for all G in G and little v in V. Actually, yeah, I've made that a little v. It's invertible, so it's big or small. Okay, so I have an idea of an invariant subspace. Okay, and then I can define this irreducibility idea. So a representation for a tilde from G to Rn is irreducible the only invariant subspaces of Rn are the kind of trivial ones, the origin and the whole of Rn. Okay, so there are no proper non-trivial invariant subspaces. So irreducibility means that whatever these matrices rho tilde do to my Rn, they mix up all the directions equally. Okay, I don't just kind of move some of the directions around and leave others unchanged. If this is the case, okay, then if I'm not irreducible, then I'm reducible, okay, and I have an invariant subspace V, and because my matrices are orthogonal, the complement is also invariant. And in this case, I can write Rn as V, the rest are V perp. And then I can consider the action of these matrices on V and its complement separately. Okay? So this is sort of now using the orthogonality, the ON property. And then irreducible representation is a large number of letters. So it is very common to find that people abbreviate this to IREP, which is just another piece of terminology that one should not be put off by. So, it's not really okay, let's do,
Your positions are lazy.
In terms of matrices, it means there's a block decomposition that's shared by
By
all
of
the
them.
elements in the group.
Yes, that's right. So every row tilde is a block diagonal matrix in 2 pieces. Yes. Okay. Okay. So let's do an example that can be extended to something that makes it look like a liquid crystal problem. So let's do S3, which is in fact the same group as D3. Let's act on R3. Okay. So I'm going to take a permutation in S3. So I'm going to take R3 and my coordinates are going to be x1, x2, x3. Okay, and I'm going to define rho tilde of sigma acting on a point x1, x2, x3 as x of sigma inverse 1, x sigma inverse 2, x sigma inverse 2. Okay, so this is permuting the coordinates, and then one can check that this is this satisfies the homomorphism property. Okay, so I put these inverses in a slightly curious way, but one can then check that if I take two permutations, sigma 1 and sigma 2, and I do those acting on x, then I do indeed get rho tilde of sigma 2, sigma 1 acting on x. Okay. So it's possible to set things up without the inverses, and then this sort of property has some inverses in it, and it's called an anti-homomorphism, I think. So this is just easier. Okay. So this is a bunch of orthogonal matrices. So for example, rho tilde for the cycle 1, 2, 3 is the matrix which is going to send either this way or the other way around. It's going to permute my coordinates, something like that. And rho tilde for the cycle that transposes 1 and 2 leaves 3 alone. Okay, so there's a collection of orthogonal matrices that combine in the way that the group does. Okay. So if I then think about this as an action, okay, this action is reducible, okay, because there's a subspace V, which is the collection of points where all coordinates are the same, okay. So it's a line in R3 is invariant, okay, and it's proper and not non-trivial. So in fact R3 can be decomposed as V plus everything perpendicular to that line. Okay, so in my coordinate geometry I have a 1, 1, 1 axis here. And then I have a kind of plane of everything that's perpendicular to that normal vector, okay? And I have an action on V, which is this line, okay? And then I have an action on the perpendicular subspace, which is that plane with normal 1, 1. Okay? And in fact, the actions on each of these are irreducible. But they're not the same. Okay? So the action of S3 on V and V perp are distinct. Okay? So the action on V is kind of trivial, okay, in the sense that everything leaves the 1, 1, 1 axis alone, so that's allowed, okay, so that's the representation where rho tilde takes every group element and maps it to the identity. Okay, that's fine. And then the action on the complement here is a two-dimensional space, and this is the kind of traditional, faithful representation of D3 that comes up in the liquid crystal context. Right. How are people doing?
You're doing all the
I'm
work.
doing all the work, you're just sitting there. How are you at home? How are you getting on?
Time for a commercial.
Should we have a phone in?
That's right. Yes. We need those audience response clickers. You know. I don't know. And there's plenty more to do. There's probably enough to do to make it worth having another session.
Oh yes, yeah.
If people would like that, rather than continuing now.
Yeah, I think
Is that a better plan?
digest where we're at. Yeah.
Okay. Well, let's
Okay.
draw a line there for today then, and I'll try and remember where we got to. We'll come back at a time when Mr. Chairman sends around another email.
Yeah, well, thank you. So in the meantime, of course, people can feed their requests to John, and
Today,
we'll see where we go from here. Okay, well,
And Ryan.
yeah. Okay. Well, thank John for the effort. Thank you.